stopped last time. Last time we considered the Majorana chain Hamiltonian related to the transverse field Ising, and the Majorana chain Hamiltonian is a special case of this quadratic in Majorana apparatus. And there is a general diagonalization procedure for such Hamiltonians, which is written here. These are just algorithmic steps. We want to represent A in such a form. And there's epsilons eigenvalues of A, and there are associated eigenvectors that are complex conjugate to each other. They form complex conjugate pairs. And out of this complex eigenvectors, we can construct real vectors. And this will be the columns of matrix Q. This is just a linear algebra algorithm to construct such a vector. Then we can define new Majorana operators or new Clifford generators, C tilde, J, which are linear combinations of the original Majoranas with the coefficients V sub j. And this is an equivalent expression. And we can define new annihilation operators that are related in the same way to the complex vectors U sub L. And this is an equivalent expression. So this is an algorithm to construct the diagonalization. And of course, the new annihilation operators are related to a new complex structure on the same vector space R to the n. And now we can actually solve this Hamiltonian. What I mean by solving it, we need to find the eigenvalues and the eigenvectors. And the most important eigenvector is vacuum. It is characterized by the condition like this. All annihilation operators annihilate the new vacuum. We can define excited states like and this will be an eigenvector of the Hamiltonian, of the original Hamiltonian, H of A and tilde equals E n times n tilde, and E n, the eigenvalue is there is a very simple formula, meaning that if we are in the ground state, then the energy is negative. There will be minus 1/2 everywhere, and the epsilons are non-negative. But if one of the Majorana modes is excited, then the energy will be increased by epsilon L. This is the standard reduction of a many body problem to a single body problem in the case of free fermions. For interacting fermions, it doesn't work. But anyway, we have this procedure of diagonalizing H of A, and we can apply it to the Majorana chain Hamiltonian. The Majorana chain Hamiltonian is H of A for a special A. And instead of writing such matrices, let me just draw boxes with dots. And this is coupling H, this is J, H, J, and so on. And of course, one can find the eigenvalues of such a matrix explicitly. Let me just say something about those eigenvalues and eigenvectors. If we simplify the problem a little bit by putting minus J and J in the corners, this means closing up the chain periodically. And the eigenvectors can be represented, those eigenvectors, Isabel. U will, which depends on Q, and it's kappa F1, kappa 2, kappa squared F1, kappa squared F2. F1, F2 are some parameters, and kappa is e to the iq. Q is a real number defined formula 2.5. So this is an ansatz for a translationally invariant system. Using this ansatz, we can find the eigenvalues by reducing this multidimensional problem to a two-dimensional problem. This is a use of Fourier transform, basically, and A of Q is a reduction of this multidimensional matrix to a two-dimensional matrix. And I'm going through those steps because they will also be used in a more general setting of constructing periodicity. And A of Q is just a 2x2 matrix, H minus kappa J, kappa minus 1 J, H minus kappa J 0, 0 times 2. And the spectrum is given by epsilon of Q. Epsilon of Q is basically the absolute value of H minus let me just say e to the iq times J. And we can plot the spectrum, which is a quasi-particle spectrum. And an important feature is that unless H equals J, there is an energy gap in the spectrum. And we can write, we can also draw a phase diagram. And there is a phase transition. When H equals J, at this phase transition, the energy gap vanishes. It's nice that we found the complete spectrum, but if you think carefully, you may notice something is wrong. Because we know that the model is equivalent to the transverse field Ising model. It should have the same spectrum. And the state here, the ground state here is this. And on the vertical line, there are two ground states. And the Majorana chain has just one ground state everywhere, except for this line, maybe. The problem is those things, because the transformation between spins and Majorana operators is non-local, and introducing periodicity in this model is not equivalent to introducing the periodicity in the original model. So let's get rid of those terms and actually solve the problem. And let me tell you qualitatively what we get. In the bulk of the system, the spectrum is the same. Of course, I should explain what a bulk spectrum is. At least I will explain what a bulk energy gap is later. But just working with such metrics, you can get a sense what bulk and boundary energy gaps are. And it's better to consider special cases when H is non-zero and J is zero. We have this picture, which means that the Majorana modes are gapped, and we can label them with tildes just fine. So the new Majorana modes are basically the same as the original ones. And all the epsilons will be equal to 2h in this case. But in the opposite case, we get a different picture. And there are pairs of Majorana modes that can be called C3 tilde. Let me put this label below. But there are also two dangling Majorana modes at the ends, and they should be identified with C1 tilde and C2 tilde. And these are called Majorana zero modes. They correspond to epsilon 1 equal to 0. So in the chain, in this case, when H is 0, J is non-zero, in this phase, the ground state is twofold degenerate because there is a zero mode, and it can come with n1 tilde, n1 equal to 0 or to 1. It can be empty or occupied. So now we have a consistent picture. Here, the ground state was twofold degenerate, and in the Majorana chain, it's also twofold degenerate. But defining a phase transition for a spin model is a bit tricky. It depends on whether we impose a symmetry or not. But for Majorana chain, this line is an actual phase boundary, meaning that when we add more parameters to the model, we cannot cross from one phase to the other, avoiding the gap closing. The gap must close. Whereas in the original model, if we add more parameters, allowing breaking all symmetries, then we can go from one phase to the other. So this is the general solution for the Majorana chain. I'll continue with a more general picture, a big picture of topological phases, and then I'll return to free fermion systems and try to build some mathematical model that eventually will turn those systems into the KO spectrum. So. We consider quantum states on a lattice in Rn, and we can consider different types of states. The simplest type is free fermion states. Specifically, we consider gapped free fermion states, such that all the epsilons are bounded from below by a number that does not depend on the system size. Of course, the second version of the Majorana chain does not satisfy this condition because there are two dangling Majorana modes at the end, and we need to deal with that. But morally, it belongs to this class. And there is a bigger class of systems. I'll explain what's new with those systems. They're called invertible. And in a moment, I'll give a definition of invertibility. Actually, I show in which sense free fermion systems are invertible and how it could be generalized to more general systems. But the idea is if we have two systems, like two Majorana chains, even if we even if there are dangling modes at the end, it doesn't matter. They are both they're both gapped in the bulk. The dangling modes are the only parts that are gapless, and the interior is gapped. Suppose that the first Majorana chain or system is described by matrix A, and the other is described by minus A. Given such a system, we can introduce coupling between two copies of the system and continuously increase the coupling. I'll explain it exactly what it means in a few moments. We can continuously increase the coupling and also continuously decrease the coefficients of the matrix A, multiply A by some vanishing factor. And in the end, we'll get a bunch of Majorana pairs which may be called a trivial system. So the idea of invertibility, given a state, there is a complementary state. In this case, described by a matrix of minus A, or more exactly, it's H minus A. It's called complementary state. And we can continuously go from H and H complementary to H trivial. These are invertible states. And invertible states are special cases of topological states. Let me finish this sequence. The last thing is gapped. Gapped in the bulk. I'll define topological states in terms of new features they provide. Invertible phases provide the following new feature. A system may be gapped in the bulk, but it may have ungappable boundaries, like the Majorana chain. And another example of ungappable boundary is integer quantum Hall effect. For example, nu equals 1 integer quantum Hall effect, which is a gapless mode that propagates along the boundary in one direction. It's called chiral mode. And this is an example of ungappable boundary. We cannot change the boundary condition to open a gap on the boundary. And invertible phases may or may not have ungappable boundaries, like the first version of the Majorana chain with j equals 0 doesn't have such a thing. The boundary is also gapped. But it may have ungappable boundaries. Topological phases may have one more interesting feature. Anyons. And this is an example. In the toric code, there are anyons of type M, magnetic vortices, plaquette excitations, and there are also E particles. And if we move an E particle around an M particle, then there will be a minus sign. Topological phases are not invertible. If we stack the toric code with another system, say another toric code, it's not possible to kill anyons in both layers by coupling them. In the sense that if we couple them, eventually we'll kill the anyons, but we must go through a phase transition where the system becomes gapless in the bulk. So topological phases may have this feature and that feature. And systems that are gapped in the bulk are not necessarily topological, meaning that they have more features that are sensitive to fine geometric details. And this is an example. If we consider a stack of toric code layers, each layer carries anyons. And those anyons cannot move from one layer to the other layer. They are distinct. If we close up the system and make a torus cross interval, the result is very sensitive very sensitive to the exact matching between the left boundary and the right boundary. If we match it with a shift by one layer, the spectrum will be totally different. If we match exactly, then there will be many copies of the toric code. If we match with a shift, there will be just one copy of the torus. So this is a non-topological thing, and another example, it's just a generalization of that example, is called fractons. So on. So there are many things, and they have some wild behavior in general. They're difficult to study. So referring to Mike Hopkins' talk, he considers infinitesimal categories which are supposed to correspond to topological systems, and invertible phases that are supposed to correspond to an omega spectrum. And these are beyond topological description. Next, let me define invertibility. And invertibility will be defined first in dimension 0, where we don't have to care about boundary modes and locality, and then I'll introduce locality. Let's take a real antisymmetric matrix. With an energy gap, which means the spectrum and we'll work with the space of such matrices. Consider two matrices, A and minus A. And we can consider the direct product by taking the direct sum, by taking the direct sum of the corresponding vector spaces. A is a matrix or an operator acting in some Euclidean space, and A prime minus A is also an operator acting in Euclidean space. And the claim is this thing is connected by a continuous path to A prime plus minus A prime such that all the matrices on that path belong to this set. They have a gap. And A plus minus A is this matrix. This can be connected by a path to an intermediate station. It's an antisymmetric matrix. And eventually to this. And let me focus on this path. We define A of theta and theta will be in the interval from 0 to pi over 2. like cosine theta. And this is a general expression. And I want this to be O of pi over 2, not of 1. This to be A of pi over 2, and this to be A of 0. So this is a continuous path, and it could be constructed for any pair of matrices, A of 0 and A of pi over 2. But we need to check whether those matrices satisfy that condition. And let's consider the matrix A squared in general. And we want that minus A squared be greater than delta squared. This is an equivalent condition. And using this formula, we can consider minus A of theta squared. And we get remarkably, in this case, the last term vanishes. And if we look at those two terms, if A0 squared is greater than delta squared, and this is also greater than delta squared, then the sum is also greater. With a minus, of course. Okay, so we can continuously connect two copies of the system. One copy should be taken with a minus sign to this intermediate system that is called trivial, this one. This is invertibility in 0 dimensions. We should consider high dimensions. Let me stay in the framework of free fermion systems for a while, including the next lecture, because this way we can do things very concretely. So when we talk about free fermion systems, we basically talk about antisymmetric matrices. That's it. And the next topic is local matrices. Let's consider some set S, and let it be a subset of Rn. In one dimension, it will be just an interval. This is our set S. And we define a local matrix in the following way. First, we define a set of points in associated Euclidean spaces. Like this point, both dots are considered as corresponding to one point on the interval. These two correspond to another point, and those two correspond to yet another point on the interval. And of course, this definition requires a choice of those points, but let me be slightly more general. Let me say that for each point, and I really mean for all points in S, but only finitely many of those spaces will be non-trivial. Most of them will be trivial. And this is a convenient setting because when we do something, we may be in a situation where there are too few points to achieve what we want to achieve. And at this point, we're free to add more points. And we're free to increase the dimension of that. It's like if you work with a rope of a finite thickness, you may not be able to tie a knot. But you're allowed to stretch the rope, it becomes thinner, and then you're fine. So it's I want to allow such tricks. So I want to consider embeddings of those spaces one to another. Those spaces can be R to 2 and sub x, and if we have some metrics for a particular choice of n sub x, we can enlarge this matrix by adding this template. And this way, the space of matrices will be made into a direct system, and when we can take direct limits. But I have not defined locality yet. So we have a set of a subset of X, and we define matrices as local matrices on S M, the collection of those spaces, and there will be a parameter R, and this is the direct product, or direct sum. It doesn't matter because everything is finite for this is the set of adjacent pairs, which is equal to the set of pairs of distance at most R. And this is the dual space, which is isomorphic to the space itself, because it's a Euclidean space. Okay, this is a definition of a matrix not relative to the boundary. We have to consider relative to the boundary to get rid of those Majorana zero modes at the end. And I'll do it a little later. Now, on the previous lecture, I mentioned two principles, local and soft. And let me just exercise the locality principle.
Here, let me answer. This is the anti-symmetric matrix. X.
It's a vector space.
It's just a vector space.
And this is a space of antisymmetric matrices. We can consider these elements as antisymmetric because we can identify my star with my, and then we can consider antisymmetry. But the next lemma does not require antisymmetry. So
again where the antisymmetry comes from, since this tensor product is a space of all linear map from my into mx.
Let me be more precise. This is the space of all matrices. And we can define the space of antisymmetric matrices that are a subset of Lm. Locality lemma. Some matrix M is R local. R local means belonging to this space, and the restriction of M to subset D, which is a ball of radius R, has a norm bounded by A. Then the norm of M itself is bounded by A times 1 plus R. Should be capital R. And the implicit constant in the big O notation depends on N, the dimensionality of the space. Balls D. Okay. And it means that we don't have to look at the whole system. There is a condition that needs to be checked for each small subsystem, this restriction, and then it will work for all for the whole system. Of course, this is a very simple condition that the norm is bounded. And to proceed with a more complex, more interesting condition, let's define local matrices on a space with boundary. So we consider S relative its boundary, and the boundary will be called S0. It doesn't have to be the whole boundary. It can be part of the boundary. It's like in homology theory. So what do we do in this situation? Let's define a margin. Oh, first, let's define the following. Instead of working with pairs of sets, it's convenient to collapse the second set to a point and consider the set, the pair S hat, which is S quotient 0, comma star. That is the result of the collapse, and this will be a metric space with the quotient metric. And we define the margin of S hat R as this set of points. And we define local matrices on S hat this is the quotient of local matrices on S over the product over marginal pairs. And the idea is that the data or the matrix elements near the boundary are unreliable, and we want to ignore them. That's why we're taking the quotient. And this definition is crafted to allow a nice definition of multiplication. When we multiply two matrices, first the locality increases. The multiplication is standard. Because the locality goes from R to 2R. And the margin also increases. And the quotient is consistent with the multiplication. So we can define squares of R local matrices, which will be 2 R local matrices. Why is it useful? Now we're in a position to define a local gap or a bulk gap. So dimension 0, the definition is more or less straightforward. It's minus a squared is bounded by delta squared. And we can put another inequality for convenience, delta to the minus 2. Now, let's extend this definition to local matrices. Say that A minus A squared, which is a 2R local, it satisfies a similar condition, but before writing the inequality, we need to restrict it to a smaller region. We need to ignore the margin. So we're restricting to the interior, excluding the margin. And then we can write the same condition. And furthermore, this condition can be imposed on smaller sets using the previous lemma. And that will be sufficient. So this way we can define rigorously what a bulk gap is. It's important that we first square and then discard the margin. The other way doesn't work.
Wonder whether physically to ignore the margin, the boundary is to allow to add an arbitrary boundary operator such that for all those there exists some local boundary coupling to gap out everything.
Yeah, you may say that. Yeah, yeah. Okay.
So
Yeah, sure.
you describe this quotient, but you don't use it over there.
Here?
Down here with this nice quotient,
Yeah,
but you don't use it.
I do.
So, because you take S minus O to O rather.
Oh, I use it in the sense that A may belong to the quotient. And when we discard the margin, it will define metrics. So you're right. I don't have to use it. But it's still reasonable to use the quotient because otherwise, well, it won't give a nice theory because on the one hand, we keep some information near the boundary, but on the other hand, we discard it at some step and we're not able to recover. Okay. This is the definition of a bulk gap, which is local. We can amplify the bulk gap, actually. We can move these two numbers arbitrarily close to each other. In principle, delta can be made arbitrarily close to 1. And to this, we need to apply some polynomial to the matrix A. We apply an antisymmetric polynomial, and if this antisymmetric polynomial is almost constant on the original spectrum, then the spectrum of f of A will satisfy a stronger bulk condition. So we can amplify. But since it's a polynomial, matrices are multiplied by each other and the locality worsens. So there is a trade-off between gap, these two numbers can be arbitrarily close, and locality. Then we can do some operations that are related to the notion of softness. And I plan to discuss three operations. Let me show you one, and I'll show you the other two on the next lecture. So the first operation that corresponds to softness is mapping one system to another system. Suppose we have an element corresponding to a point, the local matrix corresponding to a point, and we want to map this point to Rn. And we can move this point to Rn in different ways. For example, we can move it here, we can map it here or there. Actually, local matrices defined in this way with the quotient form a covariant factor, covariant functor, which means that given a map of two metric spaces, there is a map of the corresponding spaces of local matrices. Let's consider two maps, mapping this point here and mapping that point there. And we would like to connect these two maps by a continuous path. And in the continuous setting, we could do that easily. If we just consider intermediate maps. But now we're only allowed to use a discrete set of points. What do we do? First, we can break this path into little paths like this. So first we want to move this map from this point to that point, then to that point and to that point. How do we move between these 2 points? That is actually easy using that kind of extension, because we consider isometries from Rm to Rn, and we can consider pi 0. Actually, we can consider any fundamental group, and it's 0 if n is big enough. So if we enlarge those spaces and consider one isometry, another isometry, we can temporarily map to the union of those spaces, and that would not be a map from a point to a point. It will be a map of local matrices to some local matrices that here it was strictly local on a point, and there it won't be strictly local. It will have this locality radius r. But there is enough room to connect different maps to nearby points and to do other deformations. So, for example, we can map a Majorana chain to a different lattice, and we can actually deform this Majorana chain. We can compress some parts of the Majorana chain by a factor of 2 and stretch other parts by a factor of 2, and this can be done continuously. That's it. Thank you for your attention.